This morning, researchers at the University of Southampton published findings that fundamentally change our understanding of how our planet works. And what they've discovered is both extraordinary and unsettling. Earth is slowly peeling its continents from below. This hidden process has been fueling volcanic eruptions in the middle of oceans for tens of millions of years, and we never knew it was happening. Let me be clear about what this means. The continents you're standing on right now are not solid, stable platforms. Deep underground, at depths of 150 to 200 kilometers, they're being stripped away piece by piece. These fragments are then transported sideways for over 1,000 kilometers through solid rock into the oceanic mantle, where they feed volcanic activity. This is happening right now beneath the Indian Ocean, the Atlantic, and every ocean where continents have split apart. And scientists only just figured it out. The discovery solves a geological mystery that has puzzled researchers for decades. Volcanic islands like Christmas Island in the northeast Indian Ocean contain chemical signatures that look distinctly continental, even though they're located thousands of kilometers from any continent. The rocks there show high concentrations of elements like potassium, uranium, and rare earth elements that should only come from continental crust, not ocean floor. How did continental material get into the middle of the ocean? Scientists have been asking this question for years, and until now, the answers didn't add up. The standard explanations involved either ocean sediments getting dragged into the mantle at subduction zones, or massive plumes of hot rock rising from deep within Earth, bringing up ancient recycled material. But neither explanation worked for many of these volcanic regions. Some are nowhere near subduction zones. Others show no evidence of deep mantle plumes. Professor Thomas Gernon, lead author of the study and professor of earth science at the University of Southampton, explains the frustration. We've known for decades that parts of the mantle beneath the oceans look strangely contaminated, as if pieces of ancient continents somehow ended up in there, but we haven't been able to adequately explain how all that continental material got there. Now we know, and the answer is more elegant and more powerful than anyone imagined. When continents begin to break apart, they don't just split at the surface. Powerful stresses deep within the Earth trigger something called a mantle wave. This is a slow-moving, rolling motion that travels along the base of continents at depths of 150 to 200 kilometers. This wave moves at roughly a millionth the speed of a snail, but over millions of years it gradually strips material from the deep roots of continents. These roots, which can extend 200 kilometers or more underground, are made of rock that's slightly different from typical mantle material. They carry a distinct chemical signature enriched with continental elements. As the mantle wave rolls along, it tears pieces of these roots away. The detached fragments, still solid but slowly deforming under immense heat and pressure, are then carried sideways through the mantle for over 1,000 kilometers. That's more than 600 miles through solid rock. Once embedded in the oceanic mantle, these fragments stay there for tens of millions of years. Eventually, when the mantle melts in certain regions, these continental fragments melt too. The resulting magma rises to the surface and erupts, creating volcanic islands with a distinctly continental chemical signature, even though they're thousands of kilometers from any continent. The team proved this mechanism by building computer simulations that recreated how the mantle behaves when continents split apart. The results were clear. The mantle wave forms. It strips material from continental roots. And that material travels extraordinary distances into the oceanic mantle. Professor Sascha Bruni of GFZ Helmholtz Center for Geosciences in Potsdam, a study co-author, emphasizes the long-term nature of this process. We found that the mantle is still feeling the effects of continental breakup long after the continents themselves have separated. The system doesn't switch off when a new ocean basin forms. The mantle keeps moving, reorganizing, and transporting enriched material far from where it originated. Think about what that means. When Africa and South America split apart over 100 million years ago to form the Atlantic Ocean, the mantle beneath that rift didn't stop moving. Even today, 100 million years later, it's still circulating continental material that was stripped away during the breakup. That material is still feeding volcanic activity thousands of kilometers from where those continents once touched. To confirm their findings, the researchers analyzed geological data from the Indian Ocean Seamount Province, a chain of volcanic formations that appeared after the supercontinent Gondwana broke apart over 100 million years ago. The evidence was exactly what the model predicted. Soon after Gondwana split and the Indian Ocean formed, there was a massive pulse of volcanic activity. The magma from these eruptions was unusually rich in continental material, showing high concentrations of elements typically found in continental crust. Over time, this continental signature gradually faded as the supply of stripped material decreased. The timeline perfectly matches what you'd expect from a mantle wave that's most active immediately after continental breakup, then gradually weakens as it moves away from the rift zone. And here's what makes this discovery even more remarkable. All of this happened without a deep mantle plume. The traditional explanation for volcanic activity in the middle of oceans has been that hot plumes of rock rise from near the Earth's core, bringing up material from thousands of kilometers deep. But Indian Ocean Seamount Province doesn't show clear evidence of such a plume. We're not ruling out mantle plumes, Professor Jernan clarifies. But this discovery points to a completely new mechanism that also shapes the composition of the Earth's mantle. Mantle waves can carry blobs of continental material far into the oceanic mantle, leaving behind a chemical signature that endures long after the continents have broken apart. This is a fundamentally new way that Earth recycles its materials. We've known about subduction, where tectonic plates sink back into the mantle. We've studied mantle plumes rising from deep below. But this lateral transport of continental material by mantle waves operating over tens of millions of years, this is entirely new. The implications are staggering. Earth has been breaking apart and reassembling supercontinents for billions of years. Every time a supercontinent broke apart, this peeling process would have happened. Mantle waves stripped material. That material fed volcanic eruptions. Some of it got mixed deep into Earth's interior. So how much of the mantle's composition has been shaped by this hidden process over Earth's 4.6 billion year history? We don't know. And that's the point. If scientists could miss this fundamental mechanism until 2025, what else are we missing? The research also builds on the team's earlier work, showing these mantle waves can trigger diamond eruptions and reshape landscapes thousands of kilometers from tectonic boundaries. These waves aren't just transporting material. They're actively influencing geology across vast distances and timescales. This discovery changes everything. It changes how we understand ocean volcanism. It changes how we think about continental breakup. It changes how we model Earth's interior. And it opens entirely new questions about processes we thought we understood. What's perhaps most striking is that this is still happening right now. At this very moment, beneath the oceans, at depths we can never reach, mantle waves are rolling through solid rock at a millionth the speed of a snail. They're stripping fragments from continental roots. They're transporting material over 1,000 kilometers. They're feeding volcanic activity that will continue for tens of millions of years. Earth is not a static planet. It's a dynamic, self-recycling machine. Constantly reworking its materials, constantly moving, constantly reshaping itself from the inside out. And we're only just beginning to understand the complexity of how it all works. The study was published today in Nature Geoscience by an international team from the University of Southampton, GFZ Helmholtz Center for Geosciences, the University of Potsdam, Queen's University in Canada, and Swansea University. For decades, scientists have compared Earth's mantle mixing process to a cake mixer folding in older ingredients from deep within. But unlike a cake mixer, this process is invisible. Happening at depths? No. Human will ever reach, at speeds too slow to perceive in a human lifetime, operating on scales that span entire ocean basins. This is one of those rare moments in science when a single discovery forces us to completely rethink fundamental processes. It reveals that Earth's interior is far more dynamic, far more interconnected, and far more complex than we imagined. And it raises the most important question of all. If this process could remain hidden until now, what other mechanisms are operating beneath our feet that we haven't discovered yet? What other ways does our planet recycle, transport, and transform its materials that we're completely unaware of? The answer is unsettling. We don't know. And that's what makes discoveries like this so crucial. Every time we think we understand how Earth works, nature reveals something new, something that's been happening all along, invisible to us, operating on timescales of millions of years. The continents beneath your feet are being peeled from below. Material is being transported through the mantle over distances of 1,000 kilometers. Volcanic eruptions in the middle of oceans are being fueled by continental fragments stripped away tens of millions of years ago. This is not science fiction. This is not speculation. This is what's happening right now on planet Earth, and we're only just beginning to understand it. Stay tuned for updates as researchers continue to unravel the implications of this discovery, because if there's one thing this finding teaches us, it's that Earth still has secrets. Deep secrets, operating at scales and timescales that challenge our ability to comprehend, and we're only scratching the surface.